Hello everybody, this video is meant for Mrs. Rose's AB Calculus class, and it is our first lesson after the new year, so Happy New Year! Today we are learning about area approximation, and we are going to start by looking back at what we began right before exams, which was looking at total distance traveled if given the graph of velocity. All of the velocity graphs we were given originally had either horizontal lines or they had semicircles or like triangles. Basically things we could calculate the area of geometrically to get a total distance traveled in units, possibly in like miles or feet or something like that. But what we want to be able to do today is compute the area under the graph of a curve of velocity rather than like a geometric area like semicircles and triangles and stuff. So our strategy is going to be to approximate the area using rectangles. To do this, we are going to divide our interval into n subintervals. For this example, I'm going to use n equals 4. So I'm going to divide my interval from a to b into 4 subintervals, like that. Then I'm going to draw 4 rectangles using the height to be the height of the right endpoints for each of the subintervals. However many subintervals you have, that's how many rectangles you should have. Then what we can do is take and denote the areas of all 4 rectangles using r sub n, r meaning right endpoint and r meaning 4 subintervals, and we are going to have the width times the height. So for each width we're going to have a delta x, and delta x is going to be equal to whatever your difference in the interval is divided by how many subintervals you have times f of some x value. If you have 4 subintervals, you should have 4 rectangles. The Riemann sum is the sum of all of the areas of the n rectangles, and this is the approximation of the area underneath the curve. In class, we calculated R4 for f of x equals x squared on the interval from 1 to 3, and we calculated R6. Now I'm going to go through how to calculate R8. The first thing we need to do is calculate your change in x. This we do by taking the difference of the interval and dividing by how many subintervals you want to have. Well, 3 minus 1 is 2, and when you reduce that fraction you're going to get 1/4. So on our number line between 1 and 3, we want to have 8 subintervals broken up at every 1/4. So we're going to have 1 and 1/4, which is 5/4, plus another 1/4 is 3/2, plus another 1/4 is 7/4, plus another 1/4 is 2, and then 9/4, and then 5/2, and then 11/4. So using our right endpoints, we're going to have these 8 R values. So R8 should be equal to 8 rectangles with areas with 1/4 and f of those x values. So we get 1/4 times f of 5/4 plus 1/4 times f of 3/2 plus 1/4 times f of 7/4 plus 1/4 times f of 2, etc. So we have 8 rectangles. When you pull out the 1/4 and you plug in the actual function, you're going to get 1/4 times 5/4 squared plus 3/2 squared plus 7/4 squared plus 2 squared plus 9/4 squared plus 5/2 squared plus 11/4 squared plus 3 squared. So in the end, we get r squared equal to 155/16, or 9.6875. And that's how you do a right-handed Riemann, or right-sided Riemann sum. Our left endpoint approximations are abbreviated LN, and our midpoint approximations are abbreviated MN. Now, we did this example in class, so when we are going through and calculating a Riemann sum, it depends on whether it's a right side, a left side, or a midpoint. So a midpoint of with 3 subdivisions, well, we have an interval from 0 to 6. And if we want 3 subdivisions, our delta x is going to be 2. So calculating the right Riemann sum, our delta x is going to be 2, and then we're going to multiply by the velocity at t equals 2, plus 2 times the velocity when t equals 4, plus 2 times the velocity when t equals 6. And we did this one in class, so when you plug in the different values for the velocity, we're going to have 2 times 33.44 plus 20.32 plus 16.64, and that calculation comes out to be 140.8 feet. When you go to do a left side Riemann sum, it's the same idea, but you have to look at the left side. So with 6 subdivisions, we have an interval from 0 to 6, and our delta x is going to be 6 minus 0 over 6, which is just 1. So we're going to have 1, 2, 3, 4, 5. Apologize, it's not writing so clearly, guys. And our left endpoints, we're going to start at 0, and that's 0 is going to be the left endpoint on the interval from 0 to 1. 1 is going to be the left endpoint on the interval from 1 to 2. Same thing at 2, 3, 4, and 5. So our left-sided Riemann sum is going to have a delta x of 1 times the velocity at 0 plus 1 times the velocity at 1 plus 1 times the velocity at 2 plus 1 times the velocity at 3 plus 1 times the velocity at 4 plus 1 times the velocity at 5. So then all you have to do is plug in those velocity values. 20 is the velocity at 0, 32.29 is velocity at 1, and so on. When you plug all of that into your calculator, you get 149.05, and that's feet traveled. Okay. A midpoint is possibly the hardest to come up with the x values. On an interval from 0 to 6, with 3 subdivisions, we have 6 minus 0 divided by 3, so our delta x is 2. So on each of these subintervals, we need to come up with the midpoint x value to do our Riemann sum. So M3 is going to have the delta x of 2 times the velocity of 1, plus 2 times the velocity at 3, plus 2 times the velocity at 5. After you plug in each one of those velocities and multiply by 2, your distance traveled is 150 feet. If you guys have any more questions about Riemann sums, please come see me during Cavalier Morning.